Well, good morning, everybody. As he introduced us from New Zealand, I am not a drilling engineer, as you can hear from that name, but I'm going to show you some things that we've learned in New Zealand as I expand on from what I was talking about yesterday morning. So hopefully we push the magic button. Okay, so we've got a lot to get through. There's the history. We talked about that yesterday. I'm just going to rattle through the first 10 slides quite quickly because the business end of it is at the back, okay? That's where the money comes in. Is everybody's interested in money? Yep. Okay, one person. Right, so we've got a bit of history. We've been around. We've done a few things. And we've advanced from that to this. Okay? So there's a DrillMax 350B. It's a big one for New Zealand. And but we've had a lot of experience. So as I said, we're just going to get through this. But some of the things we're on about, honesty. Up front regarding costs, right? So, quality assurance, we make sure that happens, right? Prioritizing quality. We don't want to do a bad job. We want to make a successful operation. But from our experience, we prevent pitfalls, making sure that we don't cut corners, trying to find a cheaper alternative. Safety is number one for us, though. Even the small things, everything is reported. It's not the blame game, it's to learn and make sure that everybody goes home safe. And that's our number one game. So our cultural change has been dramatic in the last 5 to 10 years in what we do and how we do it, working with our client. So our reputation for safety that is high on our priority list. But also that New Zealand Code of Practice of deep geothermal drilling, okay? That prevents a lot of mistakes in the whole operation. So you've got to think about that. And we've had some results. So this is in the Philippines many years ago, one of our older rigs. It's long gone, but we have some experience there. Now we have Rig 32, and that has been looking after us quite well. And through COVID, we got through that. We managed to keep a crew on station through the challenges that brought us. But remember, New Zealand is a long way from Italy, where the parts are made. So we have to order these things a year and ahead. So it takes us quite a bit of planning and logistics behind the scenes. And we run with a very small, lean team to do it all. But you notice in the picture, 3 mud pumps. There's some other things that we're going to talk about here. Anyway, this is some of the things we do under the drilling services. And we can help you in different ways. And train people, though. And we have been invited to help in commissioning projects and things like that. So, as I said, I'm racing through these quite quickly because I want to focus on the business end. And of course, we can carry on with these things as well. Avoiding advice on environmental constraints, management of drilling operations, regular reporting, and comprehensive well completion report. That's very essential. I can go back records to 1950 and find the original handwritten records of the first well drilled in geothermal New Zealand. Still relevant. That's the records that we want to look at. We're looking for 60 years, 70 years of records or more. And from that, if we want to get into that new geological area, what is the history? Who's drilled here before? And some of the paperwork I've seen from this part of the world is quite old as well, but it gives us some indication, but we've got to build on that. So each step is a learning curve. Advancements. So with the rig, we've advanced from the triple, that was rig 27, and we now take it only, that's the time frame, 1% non-productive time. Less than that, that's our object. So that's where we're trying to drive to. I know in the Philippines, they try to do that too, and they've learnt and gaining on us. So it's a challenge, eh? Anyway, we've moved from the traditional rig to the super single. And there's some things that we've observed from it. The air drilling decreases the lost circulation, noise reduction, very important when you're working around local people. We've had to overcome working nearby to towns, and we built up a wall, sound barrier around it to help reduce that noise. Safer operation, we don't have everybody up in the mast. Those sorts of things all make difference to us, and our team morale is improved. We've also made a big leaning on the health and safety side of it. There's some statistics from the previous years. Sorry I haven't updated this slide. But anyway, we've also got the upgraded skilling system. So our particular rig can actually move on to 4 wells, set it up on one site, and also we can make sure that the maintenance and certification and cycle of every 5 years you've got to go through and test and pressure test this and change that and keep all the certification up. All the drill strings checked every two wells, those sorts of things. Everything's numbered and corrected. Our asset management system is very, very impressive. We're always learning and improving on it. We always make mistakes, but you try to minimize them. So don't get hung up on that. Learn from them. Okay, so we have a bit of a few other things going on at MB Century. I said I'm just going to get through this quite quickly. And now we've also, we talked about moving from the one rig to the rig 32 and the 3 mud pumps, 1600 horsepower. Is this all good, guys? Am I too fast? Okay. Well costs. Now this is where the money starts. Obviously, this is you can see there's an industrial area in the background. Since this photograph was taken, there's now a 75 megawatt power station built on this location. This was taken about 15 years ago, this photograph, and but we paid it, and but the terrain, we had to change some things around that particular location. But these are the cost factors you have to consider when you're planning your wells or planning your sites. Think about the terrain. I've been to some remote places in Indonesia, Papua New Guinea, Philippines, for example, and it's all very well sitting in the head office back here in, say, Taipei, but when you get to location and the boss says, oh, we're going to put it here because that's the right spot, and you've got to shift half a mountain, or you've got a landslide potentially, or typhoon, wind issues, things like that, all have to be thought about, and they all cost. Obviously, a location of existing geothermal fields, but here in Taiwan, you're going to be drilling in brand new fields potentially, right? Obviously, the cost of the well design, diameter, the water supply. We've been asked to have a look, can we use seawater? No, we're not going to use seawater for cooling water. We need clean, clear water. We pump over 3,000 litres a minute down the well during drilling. We want water to flush those cuttings back to the surface and to make sure the well is safe. That is our barrier of control during drilling operations. When we switch to air drilling, that's another subject again. But we need good, reliable water sources. Obviously, the rock formation is a challenge. That's where you start selecting the right bits, but they cost money. And then you've got testing. Minute. 3,000 litres a minute is what we make sure, at least onto the rig site. We need that guarantee. So we lay in 6, 8-inch pipelines several miles from whatever river we can get. Put a little dam in there, we have backup pumps, and you have supplies, and you have backup systems. You do not want water to stop. Water to the rig site is essential. And then we talk about health and safety, environmental compliance. They all cost money. So these are some of the factors that need to be thought about. Here's our rig layout. So that's set up for 3 or 4 wells on one pad. It's 120 metres by 60 with plenty of room to move the machinery around. So when the trucks bring in the casing and take the drill pipe, etc., it's all the top right-hand corner is all the air conditioning and cementing systems. But we've got 4 generators on this site. This is a big rig in a sense, but it can draw 4 kilometres technically. But we allow plenty of room around so that we can actually walk. And we're fortunate in New Zealand that we do have that luxury. So from there, we make things happen. A big pond there to take all the cuttings as well. So that's a lot of rock is going to come out of the ground for 4 wells. But we've set up for that. All good? Okay. During construction, we're always monitoring optimization of drilling. Okay? The weight on the bit. The ability to drill with total losses. And that really scares the oil and gas guys. That is something they're not used to, right? Got a few nodding heads. Good. But also making sure that the open hole sections are deep enough to achieve the casing pressure. So don't get too cocky and drill ahead without making sure you've got the right casing set behind you. We learned in 1960 when we nearly lost a rig down a hole because we didn't set the casing right and we had didn't have a backup plan for the pump failure, and by the time we got there the steam was coming up the hole and we lost, and that hole lasted for over 12 years at least. It blew a crater 70 meters in diameter, 25 meters deep, and roared away as a natural geyser for over 12 years. And you could see the steam on the air from 120 kilometers away. We don't want that to happen in Taiwan. So think about it, guys. Start planning, backup plan, on backup plan. Okay? Water on water. Okay? Tools, equipment, pumps. You don't want a failure. And especially you're going to be in remote locations, so please plan accordingly. While I talk about that, you can go to website and find out blowout Wairaki 204 is the well number. There's a Google site you can go to and you can see the crater shaking. Anyway, we want to prevent stuck pipe. Why? Oh, no answers. Come on, I thought there was a drilling team in here. Yeah, drilling pipe stuck is not good. Okay, so that's caused by formation issues, etc. Bad well bore geometry, or good hydraulics to clean the well of cuttings using either air or water. That's essential, right? So you want to make sure. So there's times where we're drilling with total losses going down the well, and we keep pushing ahead. It's nerve-wracking for an oil and gas guy. Sorry? Yeah, exactly. So that's what you just got to keep going through it. Yeah. Thank you for answering. Appreciate it. Obviously, we're reviewing what takes the time. Average rate of penetration, flat spots, non-productive time. Okay? From breakdown, our object is no code 8 is our plan, which is in our log system. That's when the client doesn't pay us. So we work on a day rate. Okay? From that, there is a whole set of codes, and the client pays accordingly from those codes. Now, we have a breakdown for more than half an hour, I think it is. It's on us. The client, there's a bit of wiggle room in the middle there. So the contract negotiation needs to be worked through on what's the most efficiency for the client and ourselves. Obviously, we want to do the best job, we want to be efficient, and we want to get to the next well, but do it correctly and safely. So we need to look at what is the activity that's costing us big time. How can we improve that? So let's have a look at this one. This is how we've broken down some of our jobs. And tripping is the second biggest one. Well, yeah, it is. 15.8%. So. Aha, we're going to get to that. So in New Zealand, I'll answer the question. We changed from a tricone, went to PCD bits, and specially designed for the rock formations that we're encountering in New Zealand. So our client, who is supplying the bits, brought in somebody from the manufacturer, hired them to work in New Zealand and get those bits manufactured correctly for the rock formation. So we're pushing 300 meters on a bit, 500 meters on a bit, or more. So this particular record here is actually from an older job. But that's why we're getting 40 days and we finished a well 2,300 meters deep. I can show you on the phone. No, that's fine. I'm just saying that the last well we just completed was 2,031 meters, 37 days. And our rig shifts are approximately 12 days. Sorry? Yeah. I'll show you a picture in a second. So there's some opportunities, how we break it down and why, okay? This is how we're trying to get that efficiency. And like our friend here says, there's ways and means of doing it. Let's get efficiency, okay? This comes down to a bit of planning. Obviously, I've just looked at it a bit differently and where the bigger costs are of time. All good? Okay, so now, look at that. Tripping takes 7.1 days. Let's look at those figures again, right? Now, I've been talking to people up here using tricone bits, and they're spending all this time in and out of the hole to chase a bit. oh, that's the cheapest bit. No, no, hang on, 7.1 days, look at that. That's quite a bit of your efficiency and your morale of your troops. In, out of the hole for a bit that hasn't done 50 metres, 100 metres, right? I don't know what your figures are, but I'm just being very broad-minded here that guys think about things. There's a bigger picture, and get your accountants and your financial people looking at this. Okay? They're the guys that pay for those bits and your time, but they're also paying for wages just to sit there and trip pipe. Okay, there's some of the differences. So the tricone, we only use a big diameter tricone for the first 150, 200 metres, if we're lucky, because they don't make that sort of bit on the other side. But we're putting in 10 3/4 liners, perforated liner. So the production casing is 13 3/8 and 10 3/4. So we're drilling a 12-inch hole. That's our predominant piece. So obviously that bit selection is quite important. Obviously looking at our RPM, weight on bit, hydraulics to find the best combination to be most effective in the job. And then checking our worn bit and stabilizers, making sure, and we're going to look at that in a second. During tripping, look at this, guys. Same task repeated multiple times. But with the, and people question why we went from a triple to the automated drill mic rig. We actually did studies on it, and we ended up that we were actually slightly ahead using the computerized drill mech type automated rig to actually trip out, because the pipe is actually 14 meters long compared to the 10 meter or just shorter of the other one. You're pulling out a triple, you're pulling out 30 meters, but 14 meter length. It all actually worked, but we had the safety factor. We didn't have anybody up in the mast, slipping and sliding during 2 o'clock in the morning in the rain, storms coming in. Those things have to be thought about. So this is why we went down this line, and our client helped us to drive this. Yeah, so that did make a big difference to us. Yeah, and using the right S-grade drill pipe as well. But 60 seconds is a loss of an hour and a half. Now, that's something to be thought about, because as we looked at it, 7.1 days is taken up just in tripping time in this particular example. How can we improve that? This is why I'm trying to challenge your thinking, to show you that there's ways and means of looking outside the box. And I want you to challenge yourselves and your management or wherever to make sure that you do better. But then we think about the equipment position ready to go. The next step, crew ready to go, all planning, okay? All equipment maintained. Breakdown during tripping, obviously we'll leave the open hole, right? We don't want that, so we make sure we look after everything correctly, maintain it. Scheduled oil services and maintenance on the plant is all done at the appropriate time to make efficiency, so that we don't waste time during drilling, because we don't want to leave an open hole situation. We don't want that, okay? But here, looking at this, obviously we are analysing the flat times, and that's when we do some of the other things that we need to do to plan the next steps of the well. And this is where I'm challenging your thinking. In this particular case, we ran a 9 5/8 liner. But then, how many bit changes? There's only a few on that list, but it may not actually reflect truly what happened. But it just gives you an indication of what you can do. Casing performance optimization. Yep, getting it all ready. I've seen some pictures up here of and it didn't have a catwalk on there, so we can't load all this pipe in front of you easily. To get things prepared, getting everything organised up in front of you. And then preparing the casing well run, because that takes time. And that's a dangerous operation. We've had accidents where things have slipped and not locked, or something's been put upside down, the pin wasn't put in. So everybody's got to watch each other's backs. It's not a blame game, it's making sure everybody goes home safe. BOPs, all set up. So there we are, we've got our 3 BOPs in this picture. And there's the annulus, the big 30-inch one there to start off with the conductor casing, and work our way down and slowly work our way through it. But this is planning and preparation in advance, because these things weigh 20 tonne. So they need to be lifted in at the right time and then move through. So we're nearly there. We've got mud pumps, we've got shakers, and we use 3 shakers. There's here 3 shakers, 3 mud pumps, there's 4 engines, 1 is just a backup. Staff and maintenance, we need to have the correct handovers right through there. Strict maintenance policy as well. That's very important on our equipment because we don't want a breakdown. And that's what we finish up with. So thank you one and all for your time. Thank you.
All right, so it's good to be here. It's good to see you all here in this room. My name is Tito Satria Putra Perdana. It's a very long name, right? And I promise that my presentation will be as interesting as my name. So today I'm going to present about overcoming subsurface challenges in Taiwanese geothermal fields. We're going to explore some best practices in geothermal exploration, as well as discuss cost-effective solutions that can be applied, effectively in Taiwan. All right. So as we delve into this interesting topic, this is the roadmap of our journey together for the next 20 minutes. First, I will give you an introduction about the geologic setting of Taiwan. This is very important, so that you can understand why Taiwan is very complex geologically. Right? The next one is the Taiwan geothermal landscape, what's going on right now. Right? And then we will talk about subsurface challenges that are present in Taiwan. The next one is I will outline the objective of my presentation, setting up stage for our discussion. And then this is important, we are going to show you our assessment of current exploration method in Taiwan, what is lacking, and what are opportunities for improvement. And then the next one is examples of comprehensive and integrated exploration activities, one from Taiwan, of course, and one from Indonesia, my homeland. And the last one is conclusions. All right, so let's talk about geology. So Taiwan, of course, all we know that Taiwan is geologically very, very complex, right? Why? Because it is located along the Pacific Ring of Fire. It is also located on a convergent and compressing boundary between the Philippine Sea Plate and Eurasian Plate. So the collision between these plates, results in frequent earthquakes, right? Structural complexity, and also explains the presence of volcanoes, mountain ranges, large plains. One of them is Yudan Plain right here, the one that we are going to visit this afternoon, and also hydrothermal areas. And largely, as a result of volcanic and tectonic activities, Taiwan possesses substantial reserves of geothermal energy. And this is what's going on in Taiwan right now. So basically, we have 3 types of geothermal setting in Taiwan, right? One is magmatic volcanic type, mainly here in the north, called TVG or Tatun Volcano Group. That's about 10 kilometers north of Taipei. It is a large area, about 400 square kilometers, and it has at least 20 volcanoes inside the area. The next one, go to this part, it's called extensional domain type. One of the evidences is the development of the Yilan Plain, one of the major plains in Taiwan, right? So we have 3 fields. We have Chingsui, Jiangxi, and Tuchang. And if we go down to the southeast of Taiwan, we have 5 fields that have been explored. Huisui, Hongyi, Chiban, Jinbei, and Jinbu, right? This area here is purely compressional. So that's why techtonically, all of them are very, very complex. So far, there is one project that is active in Tatun. There's 1 megawatt pilot project that belongs to Fabulous Group. There's another project in Chingsui, right? It's about 4.9 megawatt, also belongs to Fabulous Group. And also there is a 850 kilowatt geothermal power plant unit in Jiangxi that belongs to High Power. And in here in the southeast, we have a small project in Chiban and about 500 kilowatt project in Jinbu. Each of these fields is very unique. They have their own challenges. But all of them share one common problem, one common challenge. And what is it? finding permeability. In every field in Taiwan, the problem is the same, finding permeability. Where is my permeable structures? Where is my permeable zone? So that has been a big challenge in Taiwan. So that's why all the exploration in Taiwan have focused on answering this question. Where is my permeability, right? So that's why the objective of my presentation today is, number one, is to improve exploration methods to identify permeable zones and permeable structures in the complex geology of Taiwan. And then, of course, the next one is to showcase examples of comprehensive and integrated exploration activities from Taiwan and from Indonesia, my homeland. All right, so this is our assessment of current methods in Taiwan for exploration. This is based on our experience in Taiwan for more than 40 years, right? We have been providing services since 1980s. All right, so number one is developing comprehensive and detailed geological maps and cross-sections is very important. Unfortunately, some of the fields in Taiwan, they do not have a good, comprehensive, and detailed geologic map. So usually a good map, good geologic map and cross-section include, all of the lithology, structural, right? The location of thermal manifestations, locations of all wells that have been drilled in the area, road access to the area. So because with that, it will help us to understand the local geologic setting of the area, which is very important to answer our question, where is the permeable zone or structure? The next one is, of course, enhance geophysical studies through integrated planning and execution. What we observe in Taiwan is there is lacking of cohesive planning and also execution method when it comes to geophysical studies. So mainly geophysical studies are conducted by different parties, using different tools, different equipment, and covering different areas. So there's no integrated effort, and this will increase the uncertainties of our interpretation, right? So that is something that is lacking and we need to improve. The next one is development of integrated geophysical model. So we have gravity, we have MT, we have magnetic, and EQ. Let's try to integrate them, process them together, joint inversion, interpret them together, right? To decrease all the discrepancies and also to have a good alignment across all of the studies. Then the next one, of course, we want to integrate all the data, geophysical, geology, geochemical, right? Through joint interpretation to support geothermal conceptual model development. This is also something that is lacking in some of the fields in Taiwan. Because good conceptual model will provide us with more confidence when we want to put our well, right? And after that, after we have a good conceptual model, then we need to test that. Don't stop there. We need to test that. Of course, we're drilling well, right? If the data of the well support our interpretation, that's good. If there is disagreement, then we need to update and refine our conceptual model using new data. So this is the key. We integrate, we test, and then we improve, modify. Again, we integrate all of the data, we test them by drilling, and we update or we improve our conceptual model. Again, to answer that question, where is my permeable structure zone, where is my reservoir, etc., etc. Right? Okay, so I have two examples. One's from Indonesia. It's called Ulai Geothermal Field in Sumatra. It's located in the southwest of Sumatra Island. So now it's at the final stage of development. It's 2 times 55 megawatt. It's a quite big field. Right? This area is located in a very complex area. It's not just compression, but there's also big fault, crossing the field, the Sumatra fault zone, right? So permeability in that area is also associated with fractures and faults. So to understand the development of those structures is very important. And then the good thing is exploration activities were strategically planned and assessed during integrated approaches, using integrated approaches. I'll show you examples of that. And then borehole images. So they also collect many well data, usually borehole images, to understand development fractures and faults in the subsurface, and then they try to tie with the surface map, right? And then after that, the conceptual model of the resource has been consistently tested and refined with the acquisition of new data. They have been doing this study since 1970s, and they always update the conceptual model once the new data are coming in, And then these evolving models has guided them, well targeting and also field development strategies, where to put your production, where to put your injection wells, right? And where to drill next, etc. Okay, this is the map, geologic map. It's very detailed, as you can see here. All the faults are mapped and named, right? All the lithology is carefully mapped as well, right? All the thermal manifestations are placed on the map. They're like a nice correlation. We can see that some of the manifestations are associated with faults. So from this one, we can see that okay, there's actually a good relationship between your structure and your thermal manifestations. They also established this good stratigraphic column to understand age and also the relationship between rocks in the map. And then here they also create a very good geologic cross-section. Not just from surface data, as you can see, there are about 21 wells. They use each well data to create this cross-section. And this has improved the drilling success rate in the field quite significantly, right? The next one, not just that, so structural map from the surface, they also try to test that using borehole image from all the wells. Try to understand, do they show a good agreement, from the surface and subsurface, right? What is missing? But overall, there is a good agreement between subsurface data and surface data, right? They also run an EQ to understand the which fault is active, right? So as you can see here, there are some micro-earthquake events that are associated with this fault here. And mainly, the production is setting this fault rate, which agrees with what MEQ tells us. This is gravity data, as you can see. This is a low density anomaly that is associated with fracture development, right, from surface data. And what happened is, actually, this is proven by drilling. So everything here is the reservoir, right? Empty data also show the same thing, same kind of shape, This is a moderate resistivity anomaly, just represent this zone right here, which is your reservoir. So MAQ, geology, gravity, empty, they show the same thing. We integrate them, we get more scoring, we get more confirmation, right? Our confidence level is increasing significantly. So by that, they can develop this very good and very comprehensive geothermal conceptual model, right? Where's the outflow zone, where's the reservoir zone, which part of the zone is hot, which part of the zone is not hot, right? So where to put your wells, production, injection, etc. So this is one of the best examples, right, from localized geothermal. The next one is, of course, from Taiwan, from Tuchang. This map is created by CPC. It's quite detailed. There are some geologists in CPC that are, mastering in, geological mapping of Taiwan. Those guys mapping the Tatun, Tuchang, Renze, right? These are quite good area as well, quite good map, good faults information, thermal manifestations, well locations, right? Different fracture zones, right? Lithology, and as you know here, they also run FMI data of some of the wells. Just want to confirm whether what they see on the surface is supported with what they see in the subsurface. And the result is quite good, that what they observe in the subsurface support with what they observe in the surface. Right? There's a good correlation between the fault development here in the subsurface with the fault development on the surface. And even here, we could put a major fault zone based on subsurface data, which actually correlated to one of the faults here on the surface. And that fault is one of the major faults, that associated with the good reservoir. All right, so the conclusion, number one, Taiwan is situated within a structurally complex geological region. All know that. The challenge is, to identify permeable structure and zone, and it's the complex setting. And there are significant opportunities for growth and improvement in understanding the geological context and its link to permeability, as I mentioned earlier. And then exploration activities should be strategically planned and evaluated through integrated approaches. And exploration results will contribute to developing a robust conceptual model, which must be tested and continuously refined. Again, integrate, test, improve. Integrate all the data, test that by drilling, and improve our conceptual model. That's all from me. Thank you.
I'm very honored to be here today. My name is Yuki Maehara. I'm working for SLB based in Tokyo. And today, I'm going to talk about, how, fracture is evaluated by using borehole data. So I'm lucky because, right after Tito, it's basically, very continuous story. Basically he's talking about a lot of geology. And I'm talking about more like detail how to evaluate, like a fracture by using borehole log data. But unlucky part is, my presentation is right after such powerful presentation from Tito. So please expect, your expectation is, adjust to my presentation. Also, another lucky part, I have my colleague to co-present today. He's a Chin Lee. He's working in SLB in Taiwan, Miaoli. So I'm, present together with him. Okay, let's begin. So as here, everyone knows about, geothermal, and everyone is expert. So we have a multiple different type of, geothermal reservoir type, like, sedimentary, basin, also conventional hydrothermal systems, and, next generation geothermal, EGS, AGS, like closed loop, right? So by just looking at this illustration, you can see that in reservoir part, like a lot of fractures, sedimentary part and, conventional geothermal part. Basically, we need to understand how Tito also presented. We need to understand, how, fracture it is because, we need to have fluid flowing in through the reservoir, through the fracture. On the other hand, next generation geothermal, we don't have fracture here, but we need to understand fracture. Why? Because, natural fracture for fracturing, hydraulic fracturing, makes some, sometimes harmful. So before hydraulic fracture design, we need to understand how, natural fracture is distributed. And same things happen to closed loop. Because if you have, natural fracture to permeable, your, fluid circulating this closed loop will be, leaking out. So this is why even though for next generation geothermal, it is very important to understand how, natural fracture is distributed. So, how we can do that? But we have actually, a lot of challenges. As Tito said, we have like geology complexity. This is very generally, any fracture reservoir, we have a lot of heterogeneity. Like when you have a drill here, you have nice in production, but doesn't mean next location have also like a nice production. It's very heterogeneity. Why? Because fracture distribution is caused by a lot of different geological reasons. Some fracture is initiated by fault, or like bending stress, or sometimes intrusion. Unless you understand all this, all the elements, you don't have a big picture of fracture distribution. So how we can tackle this challenge? We need to have data measurement. So in terms of data, I split into two types of data here. Like one is borehole data, such as like a variable logging data, coring data. So the other side is surface data, such as geophysical surface survey data, such as magnetotelluric or seismic, to understand wide area of geological structure. So to combine this, we can make fracture modeling for subsurface. Then we can design where we should drill, which azimuth, how deviation. And by having this modeling, we can reduce the uncertainty from the geology. So now today, we are more focused on like left side, borehole data. So like borehole data here is, I'm more talking about the variable logging data. Today I'm going to focus. This is a typical logging program for the geothermal reservoir characterization purpose. Pressure temperature spinner, which is fundamentally we need to measure temperature in downhole. And gamma ray resistivity, this is crucial for the, fundamentally we need to have depth control. And borehole image log, sonic log data, and density. This is more for fracture understanding and resource evaluation. So how this logging measurement works. I pass to Jian.
Okay. Hello. So my name is Qing'an, and I'm one engineer here in Taiwan. So as you can see, like most of the open hole logging for those geothermal well in Taiwan in past 5 years was done by me. So I think I can, confidently say like our technology can be helped to like not just CPC or like a GSMMA, but all the stakeholders in Taiwan. So as you can see, we have a FMI, like a borehole image log. It's like 4 direction with caliper, and each arm we have like 24 buttons to cover like around 80% for 8.5 inch open hole. So it's quite good. You can adjust this caliper size based on different hole shapes, and like sometimes if you have sometimes you have a big washout, or like the hole shape is kind of not roughly, so it's a good technology to run in the like geothermal wells in Taiwan. Aside from that, we have a Sony scanner, which is like an advanced dipole. We can provide a monopole dipole and also Stoney wave to cover the well bore. So together with our FMI and Sony scanner, we can provide our advanced technology by our digital teams. So why is important? Like as this slide showing, we have a lot of fracture in the geothermal zone. But how can we identify this useful or not? Right? This is quite tricky because you can see from the figure, like even though like if you drill well, you can have an induced like fracture caused by the drilling, right? So how can we identify that it's useful or like is already the fault zone already there? So first of all, we pick up the all the dipping from the FMI image, and then we can identify together with the Sony scanner Stoney waves. So combined with this FMI and Stoney, we can telling you like okay, this is from here. This is the like actual fault zone which can with penetration. So this is quite useful for all the like geothermal, especially the new field in Taiwan. So in short, like if there's like not much data in the new geothermal zone or like geothermal area we're going to be exploration, we suggest to run this FMI sonic scanner together to make sure you find the correct zone, because as we know, like most of the geothermal fields, our target is to generate the power, right? So to make the generation like more economic, we need to know which zone is like the perfect zone to generate like to produce the water, the hot fluid. So this is very important for the stakeholder here, like potential stakeholder here in Taiwan.
Yeah, thank you, Chian. And this is like some fracture analysis conventionally done, but we can do more. Like how we can do. Like this is another application using sonic data. Like basically we use same tools, same measurement of same tools using same for sonic measurement. But this sonic logging is actually also measuring some long duration of listening time. So meaning like we not only have directional wave like a P wave, S wave, but we have actually like a reflection wave is also recorded by having this tool. So in this means that we measure the sonic waveform can be analyzed like a similar manner of like a surface seismic data, such as like a migration and then eventually imaging. So we can observe some like a reflection wave from this sonic waveform field, like a P2P or P2S or S2S and SNP. So there are like 4 total modes. That reflection wave is can be is majority is basically reflected by fracture if there is some natural fracture there, right? So meaning like this measurement of this reflection event, meaning we can mapping out where fracture it is, even like a far field. So this like depth of investigation or area to investigate it is actually far. It's big compared to conventional logging. So this is actually up to like 50 meters from wellbore. That is amazing achievable by having this 3D far field sonic. And the other approach to be considered is geomechanics. I think we have a massive presentation about geomechanics maybe in later today this morning. But I like to also brief about how this geomechanics approach also works to evaluate fracture. So having like core data, drilling data, or other basic log data, especially density, and plus together with sonic data, we can analyze a mechanical earth model, like geomechanics property of the formation every single depth, meaning like a rock elastic property, rock strength, and pore pressure. And by having this model every single depth, we can apply geomechanics application, such as like a drilling wellbore stability, which is good for drilling engineer here. Also like a fracture stability analysis. So this is more crucial for fracture analysis. Why? Because as Chian explained few slides before, by having like a borehole image log, we can observe like a fracture cutting across the borehole, right? Just near wellbore. But the real challenge is from here. Now we have borehole image log, but too much, too many we can observe. But what we want to know is which fracture is really effective, really permeable, right? This is, real challenge after you get the data and start processing. So this is, like a nice approach, amazing approach, from geomechanics analysis. So we have, a lot of fracture picking up by, like a borehole image log. And from, geomechanics, we can know about, stress direction and stress field. So you can imagine that you have a fracture path, and then you press vertical. This fracture is there, but it's stable, right? It doesn't move. But if your fracture is, is steep line like this, if you push vertically, this fracture can be slip, right? Which is we call unstable. So we analyze, stable fracture or unstable fracture together with fracture azimuth and dipping, as well as stress field. We can understand which fracture is unstable, most likely open, right? That is, most likely this fracture is only can make the feed zone for geothermal, right? So Today, we are, presented about the different type of, fracture analysis, but it is very important integrate together to find out one, answer, right? That is basically reducing of the uncertainty. Just if you rely on just one measurement, one way to approach, you have some, a lot of uncertainty. But if you have, multiple approach, multiple, measurement, we can narrow down into one answer. So that is, that is what we do in geothermal, reservoir characterization. And this is one of the case study from Japan. So this is, geothermal, hydrothermal, geothermal, exploration wells. The depth is around, 2 to 3 kilometers. And we take, borehole image log and advanced sonic log and density. And we analyze, fracture picking from image log. And then you see, you have a, borehole geologist could give a lot of, like fracture. Oh, where is, fracture is permeable? She don't know, right? Now, we have, sonic and density. Okay, now, okay, we can analyze like a fracture strongly, or like we have actually, few reflection wave here. Okay, based on this data, some, the fracture is, like here and here is most likely, fracture aperture is high and then permeable, right? Then now, we also apply geomechanics modeling, like, rock strength, elastic property and stress field. Then by having this, fracture azimuth and dipping, then we can, classify, which fracture was actually unstable, most likely open, right? Then, we can, eventually we can narrow down, this three zone is, the more primarily, generate the feed zone. Then from, consider with, drilling parameter, then we have like a mud loss is like nearly here. Then, okay, that should be corresponding to here. And then if, secondary, thirdly, if operator want to complete, we can suggest this is second part answer. And just a, case study I want to share today, this is also from Japan, geothermal exploration wells. We, in these wells, we log like image log and advanced sonic log in dipole sonic. And then this is first time, attempt 3D far-field sonic measurement and analysis in geothermal well in Japan. So we take our data and then we process and then, migration and then make an image. Then we can, imaging like 60 meter, even from, well bore. And then you see that in a very clear, reflection event. And, and then this is basically measurement and result, right? And then by having, together with, FMI, borehole image log analysis result. So we interpret this, this is basically, like a fault and the previous, fault, composed by like ancient, ancient era, fracture. So currently this fracture is actually filled up, but, this zone is, basically fracture zone, generated in ancient era. But right now, this fracture unfortunately already filled. So it didn't really connect to, real permeable zone, in this well, but we could, do, nice imaging using this, sonic log data. So this is, what, I and Chian want to, present it today, more technical. But in Taiwan, as, Tito presented, case study, from several fields, we have, very, very long history with a national oil company here in Taiwan, more than, 40 years. And Chian is here. And now, we have another success, milestone, in Taiwan actually. So this was, very, very new news here. So, the day yesterday before, we had, like a MOU signing with, NCKU here to accelerate more, our contribution to geothermal, development in Taiwan. And, this is, very, very tremendous, achievement, to open new era for new history for SLB Taiwan to, support your geothermal project. So this is, very fast, success case out of, NOC. But, we are open to, if you have any, if you have any other project, you want to collaborate with us, please, please feel free to reach out to us. All right, so that is, conclusion. So basically, today, we present about, how formation evaluation in geothermal and, go through the few case study from Japan. And we are looking forward to work with you, in near future. Thank you so much for your attention.
Good morning, everyone. My name is Nick. I'm the Sales and Service Delivery Manager for Drill Bits based out of Bangkok, Thailand. And just today's presentation, I'd like to go over, essentially our hybrid drill bit. We call them Baker-Hughes called the Chimera bit. And also just our portfolio of drill bits and our experiences in geothermal applications in several areas around the world. All right. So we as Baker Hughes, we've had experiences in drilling in geothermal wells. Typically, these are metamorphic rocks, volcanic rocks. I'm hearing very similar themes here in Taiwan, where the northern part of the island is predominantly volcanics. The southern and eastern side is typically metamorphic. So we've had some, hybrid drill bit experiences in Indonesia, Japan, some PDC designs, designed specifically for volcanic drilling with the Utah Forge project in the USA, and also been involved in some quite hot and hard wells in Europe, right, in Iceland and Finland. So we have a complete portfolio covering, from PDCs all the way to rock bits and somewhere in between the hybrid drill bits, right? Hopefully, one key takeaway I want you guys to take from my presentation is that bit selection is critical for any drilling project, right? So it comes down to really identifying what your geological hazards are from a rock strength formation, what type of rocks you're drilling, how homogeneous or how heterogeneous your rock formations are in the wells that you plan to drill. And essentially, based on this information, you can actually cater the drill bit design, whether it's a PDC bit, a hybrid drill bit, or even a rock bit, to address those solutions, those issues. So, as you know, generally speaking, even in oil and gas and geothermals, wells are getting deeper, they're getting harder, you're drilling in tougher rocks. And this is where the hybrid drill bit, the Chimera hybrid drill bit, could potentially be a potential solution. So this technology is, I would say, quite mature now. It's over a decade old. We started the first generation commercialized back in around 2012. And essentially, as of today, we are on the 6th generation of the Chimera hybrid drill bit, where essentially you look at multiple factors in the bit design and material selection to try to improve the rock bit. So here on my next slide is things that we would typically focus, when we design a drill bit is, how do we lay out the cutters to address the challenges in the application? One thing that we did find with previous generation Chimeras was that a weak point would be the outer area of the drill bit, so the bits could come out under gauge. That's something that's been addressed. We looked at materials in terms of the carbide selections, the shapes, and also the cutters as well, right? The diamond part of the drill bit. And now we also look at creating digital twins of the bit designs, where we can actually model them in an internal software, right? So that we can kind of like test the concept before we actually manufacture the drill bit. So some key things, like I mentioned earlier, from jumping from the 5th generation to the 6th generation, is that we further optimize the cutter, the PDC cutting layout of the drill bit here. Looking at, manufacturing, be able to get more blades to center. This is quite important in hard rock drilling. Maximizing the shoulder coverage with the feature we call the shadow cut to ensure that, the bits stay engaged. Have a higher probability to stay engaged when you drill in these tougher formations. And we also created a kind of like a cone guard mechanism design, right? Where essentially if you do have a seal failure, you reduce the risk of actually losing any cones downhole. So at least if you do have a cone failure, when you trip the bit out, the cones have a higher chance of actually still being part of the drill bit as well. So yeah, this is just a more, I guess, focused feature of the cone guard here, where essentially, as you can see, if there's any failure in the seals of the cones, mechanically it'll be still part of the bit. Oops, sorry. And here is just an example of like our digital twin software, where we can, design the drill bit, a concept, test it out, see if it's addressing the issues that we're seeing, whether or not we need to tweak the design. One thing we can do internally is that we can make the hybrid drill bits act more like a PDC, so you can potentially drill a little bit faster, or act more like a rock bit, right? A tricone bit, whether you're having more challenging or harder formations. So it's, again, it comes back to identifying the issues that you're planning to drill and then optimizing the bit selection and the design. So this is a typical process we would follow in terms of this, right? We would try to identify the challenges, align the challenges to the bit design, run the simulation to see if our concept actually will work, and then verify it in the field. And then from there, we would then take all that data back and look back at these drill bit designs and see, okay, is there anything else we can do better from this design concept? All right. Any questions before I move on to some of the case histories? All right. This is typically how we would nomenclatureize our Chimera hybrid drill bits. So you can see number 6 is the 6th generation. We have identifiers to confirm whether our seals in the cones are elastomers or metal. And then you obviously have the cutter size, blade counts, and then the cone counts as well. All right. So one case history is from Utah Forge. This is actually a PDC bit design. As I mentioned earlier, Baker Hughes, we designed I believe it was a 7-bladed and an 8-bladed bit design optimized for the granite drilling in Utah Forge, where essentially this was run on all the 4 wells in that project. And as you can see, the wells, the first well drilled is the red line, and with each iteration of the bit design and also other improvements in the project, essentially they were able to reduce the on-bottom drilling time significantly, right? And this is like a continuous step process involved. So, you have to be very dynamic in this industry, learn, and apply those learnings. I think that will be the key takeaway here. Next, I'm going to move over to somewhere closer to home here in Taiwan, Indonesia, where we have, I guess, 2 key applications in Indonesia where we drill through volcanic rocks in South Sumatra. And we have some metamorphic applications in North Sumatra. So one of the applications in Indonesia, we're drilling to breccia, tuff, and andesite, right? This stuff can be quite nasty. You can really break PDC bits, roller cones, so typically drill very slow through them. The unconfined compressive strengths can be upwards of 25,000 PSI. The rocks are coarse and they're quite cemented, making them quite abrasive, hard. And lastly, it's also interbedded, right? This is not good for a drill bit. Typically, the ideal environments is homogeneous formations, keeps things steady. But whenever you go from soft to hard, or from hard to even harder rock, that's where you can get really some real challenges and cause some issues. So the chimeras typically would work by pre-fracturing the formation, and then the PDC cutters would then sweep in. Yeah. So then we would model this, adjust the percentage of how much the rocks are cut by the roller cone part versus the PDC part. And based on this, we saw significant improvements in both durability and our rate of penetrations, right, in Indonesia here. So we essentially, in the 17.5-inch section, we saw about 20% improvement in distances drilled and a 74% improvement in rate of penetration versus your conventional rock bits drilled. In the 12.25-inch section, we were able to double the time spent on bottom, 100% improvement in the distance drilled, and then about a 45% increase in rate of penetration rate versus conventional roller cone bits. All right. Another application in Indonesia is metamorphic rock. So this will be applicable to, from what I understand, the southern part of Taiwan here. So this is in North Sumatra. But the top layer is interlaid with quartzite, so it's a little bit mix of volcanics and metamorphics in the top hole section. But as you get deeper into the well, you're actually drilling into some quartzites and phylites, right? This can be very abrasive and very hard. So here, the Chimera and the 70 Navid section, we're essentially able to drill about 260% faster than conventional PDCs that were run in this application, and just slightly faster than the PDC bits, essentially. But essentially, you're getting more efficiencies because you're actually spending more time in the hole and less time tripping, and also less risk of the bits coming out under gauge, right? So you have better borehole quality. For the 12¼ which drilled into the quartzites and felsic intrusions here, the drill bits here, we saw about 69% farther distances and 30% faster ROPs versus the conventional PDC bits that they were historically running in this area. Right. Moving on to Japan. So we had a very successful campaign in Hokkaido several years ago. I was actually personally involved in this project and the selection of these drill bits. So the challenge here, we were drilling through some igneous and volcanic rocks in Niseko area, Hokkaido, Japan. Not a very complicated well profile, just J-shaped, about 2,000 meters MD. The key thing here was that they had a very narrow window of drilling, right? Because they had to drill only during the spring and summer and basically demob before winter time. And this well was happening during COVID, so that added extra complications. So historically, they would run PDC bits to no success. They would bring these out. Roller cone bits would do the job, but at a very low penetration rate. And based on COVID-19, this operator essentially reduced their well count from 2 wells to 1, right? Because they didn't think they were able to be able to catch up the time period. So I worked with this operator to essentially select the drill bits involved. We looked at design concepts. We did some laboratory testing as well, just to ensure that what we were selecting was correct. Just generally speaking, the bit aggressiveness of the hybrid drill bits, unsurprisingly, is somewhere between a roller cone bit and a PDC bit, right? And this can affect, your rate of MSE. So typically, your PDC bits, your roller cone bits are typically more efficient, but slightly slower. PDC bits can require a little bit more energy to break rock, but you can drill faster. And it's just trying to find that sweet spot in between. Whether that's applicable to the application or not really requires us to actually do a study and propose a design as well. So in our lab testing, we get some rocks set up in our drill lab in the Woodlands, Texas, actually putting different types of rock strengths, combining them, and essentially just running the hybrid bits versus PDC bits just to see how they respond, right? When I say respond is what is the torque signature, what are the ROP signatures here. And the key takeaway I want you to get from this slide is that typically you would see smoother torque responses with hybrid drill bits. And that's very good for drilling, because that essentially means that the energy you're putting into the drill string is actually, most of that is actually being spent breaking up the rock. So based on this Japan project, I actually leveraged a lot of the historical data run in Indonesia for the bit selection here. We did tweak the design slightly on some of them. And essentially, we came up with this 17.5-inch hybrid design here. This, you could probably say, is a more aggressive Chimera design, meaning that it will probably act more like a PDC, given that the top hole formation was slightly softer. And then as we went deeper into the well, we went into more conservative designs, right? Making the Chimera act more like a rock bit, but still having some of that PDC potential to catch that ROP where needed as well. The wells were relatively hot, so we leveraged the metal face seal technology that we have to ensure that we reduce the risk of seal failures. And it was very good to see that, once we completed the project, the operator was able to get their second well back online, and essentially we doubled the ROP in all of these sections, resulting in about savings of about $2 million here. And yeah, these are the pitfalls from that Japan project. So yeah, that is it for my presentation. I'm hoping that, we can work more closely in Taiwan, select the correct bits for the right applications here, and then, yeah, thank you. Any questions?
Thank you so much, Nick, for this comprehensive overview of the characteristics of the Chimera drill bit. So we still have 4 more minutes. Any questions are welcome.
Well, actually,
Okay.
So you say that maybe the geologic setting and the thousand volcanoes seems like somewhat similar to what Sumatra has.
Yes, that's correct.
Yeah. So like when you use a camera bit, you said that you can like adjust it or like choose the select the
Characteristics. Yeah, yes, that's correct.
So when you use the Sumatra, when you drill in the Sumatra formations, do you use a bit that's more similar to like PVC or a triangle?
So for the 17.5 inch, it's more of a PDC type bits because the formations still don't firm up that much. But as we go deeper, the designs become more, lack of a better word, conservative, right? So we had to prioritize durability more than RP potential. The thing is with drill bit design, there's always a little bit of compromise, right? If you want to go fast, sometimes you can't go very far, if that makes sense. Yeah. So it just really depends. And I think if we look at the formations in Taiwan, we would definitely need to sit down and see how different or how similar it is to Sumatra, for example, in terms of rock strength, how interbedded or homogeneous the formation is as well, because that can affect how we select the design to be run. I'm hoping that answers your question.
Yeah. So like for basically when you use a camera bit, you have to have the requirements for using a bit, right? I mean, you have to have the right equipment and tools to use those bits instead of like because using a tricone is easier.
Not always necessarily, but that is something we can always work with, right? To determine that, the drill string, for example, and the drive systems used and the rig is able to at least deliver enough power to ensure that we are maximizing the drill bit. So I guess just generally speaking, for example, when you run a Chimera bit and you compare it to a rock, this is just a general simplification from my experience anyway. You can run maybe between 60 to 70% weight and bit requirement for a rock bit at the same size, right? But then versus the PDC bit, you'll definitely need less weight and bit to achieve similar ROPs. So you're right. It is a holistic approach to, right? It's not just selecting the drill bit and then everything will go well together. You have to look at the full picture.
Okay, we can take one more question.
Thank you very much for the presentation. I have like a small question.
Yes.
So the bit life
Yes.
of the Chimera.
Yes.
So the PDC basically when the RP drops then we pull out, right?
Mhm.
For the tricones, more like revolution count.
Yes.
With the Chimera, which one do you need to take in consideration?
Both. So you'll need to look at your seal life. So for example, in Indonesia, we actually have a reliability curve for the Sumatra fields. We know that once you hit a certain revolution, you could potentially trip the Chimera out. Secondly, you also need to look at the response downhole, right? What changes you're seeing with torque. So for example, if you're drilling a Chimera bit, you're approaching your hours that you set a baseline, and let's say you see a sudden increase in torque and an increase in ROP, that could potentially be a signal that your cones are locked and the PDC part is doing the cutting. And that's why you'll see a spike in ROP and torque. Does that make sense?
So typically, right?
Yes.
Tricom bid lasts for like 3-4 days.
Mm-hmm.
With a Chimera, that's even pushed like more.
More, potentially more.
Potentially
Yes,
more.
yeah, potentially more.
But-
It'll vary application to application.
But with the anti-drop cone system,
yeah.
You can actually drill until you get the anomaly, or
Yes, you can typically drill until you get that anomaly, but then once you see the anomaly, then I would recommend a trip right away because you know once the cutting, I guess there's two ways that you can lose a cone, right? One is from hours drilled, and then the other one is that your cutting structure just fails, right? You actually eat into the body of the drill bit. So yeah, typically you see an anomaly, it's typically time to trip.
Now, after the inputs we had today from our friends from New Zealand, and then the geological logs, and then the choices of the bits, those output from the previous speakers are actually the inputs that we have as a rig contractor. How deep the geothermal well will be, what pumping requirements would the client require. One said, Mr. Adams mentioned about 800 gallons a minute or about 3,000 liters a minute. How many PSI would that be when we come to the bottom of the well? Now that what dictates us in choosing what rig equipment would be fitted for that particular well. Now that is where Thermoprime would come in. With our experience when we were conceptualized, when we were incorporated in 2011, we began with us deploying as a crewing contractor to the rigs of our clients back then. And while we were doing it, we were busy exploring the opportunities outside the country, outside the Philippines. We looked into Africa, we looked at opportunities in Kenya, Tanzania, Ethiopia, Latin America also, El Salvador, Nicaragua, Chile, and Peru. And we were pleasantly surprised that Taiwan is becoming more and more aggressive in your geothermal aspirations. And with the experience that we had back home in geothermal steam production, we believe that it's best that we can share, we can interact, what we can offer. That's why we brought a lot of people back home. They're seated there at the back for us to consult with. It's one of them. That's Dewey. Okay. What makes us unique is that we are vertically integrated with our client, Energy Development Corporation. We're of the same senior managers. And we are also aligned with the values of our parent company, construction company. Our crew, our specialists are also endowed with disciplines arising from us as early as 1976 when we were first working with them in the geothermal drilling of the Philippines. That's why, as we have mentioned before, it's best that we can share what we know for achieving the geothermal aspirations of this country. Accordingly, we will begin our story with how we did it back home, starting from 1976. And then we will have a discussion on how we manage risks that will eventually guide us in selecting perhaps the best drilling or contracting strategy for organizations here to choose from when you start getting busy with your strategies. We first came into existence with deploying crews back home to the existing rigs of our client. Now we eventually acquired 2 more rigs, followed by 3 more rigs. Now we have had consulting experiences with a Japanese engineering firm in Kenya. So that's what we call capacity building. We had capacity building in Kenya. We deployed a team of specialists there, a drilling engineer, a tool pusher, a maintenance supervisor, a safety specialist. That's what we did there. We trace our roots as early as 1976 when PNOC has had about 9 rigs operating back then. That is a government-controlled organization. We have back then a PNOC Energy Development Incorporated. Now, in 1983, that's where the Philippines became second ranking in terms of geothermal capacity in the world. Now, PNOC EDI eventually became into PNOC EDD, Energy Drilling Division, in 1983. Now, came 2007, we were privatized. Previously being government-owned and controlled, we dropped PNOC and then we became Energy Development Corporation under first gen. Now the two divisions of drilling, the well designers, that's one, and then the drilling people, that's another, they were merged in 2008. They became the Well Construction Group. That's still under Energy Development Corporation. So that's our story. And then in 2011, Thermoprime Well Services was formed. We were rebranded in 2016 as Thermoprime Drilling Corporation. Since 2011, we have completed about 220 projects already, combined drilling and workover. Majority of them are from the largest two developers in the Philippines. Combined together, that's about 98% of the geothermal capacity of the Philippines. We drilled as deep as 3,200 meters. In 2022, we drilled 3,300 meter well in about 24 days. That's what we finished it. And then, no, in 23 days. And that is immediately followed by a 3,600 meter well in 24 days. So one record is immediately superseded by another record. Now that can be done if we have the right equipment, favorable geological formation, if we follow the well design, if we choose the right bits as mentioned earlier, we adhere to the geological logs and the well design, as Mr. Adams mentioned, one guideline, useful guidelines, the New Zealand code, and if the crew is competent. That's where human resources would come in. Proper training, proper competence, and lastly, the rig has to be reliable. How many percent downtime? It has to be improving well after well. Okay? Now, that's not always the case. That's not always a walk in the park. The 3,300 meter well in 23 days, 3,600 meter well in 24 days, we have had shares of nightmare wells also, of wells from hell. A 2,700 meter well took us about 4 months. We finished that. We had to complete it. The client is requesting us. Cost is piling up. And then we heard it's now producing at 16 megawatts. Now, that's not always the case. A well as deep as 2,700 meters still being pursued for 90 days, the client sometimes has to give up. It happened also. That's included in the count that you see. So that's a combination of success stories and the challenging ones. In any case, none of them is a total failure because unfinished wells or wells that took so long is still information for all of us to improve. Equipment-wise, manpower-wise, safety-wise, logistics-wise, and engineering-wise. So it's still worth pursuing them. That is the wealth of our rig crew. We have had experience in operating mechanical rigs, SCR rigs, electric rigs, variable frequency drive rigs. These are the previous rigs. All of them are decommissioned, but the experience stays within the crew. Now, this is our current rig fleet. We have 2 rigs of 2,000 horsepower, 2 rigs of 1,500 horsepower, and lastly, for compact spaces, 1 rig of this one, 1,000 horsepower. All of them are deployed back home. So that's how aggressive one of our clients are. That's our asset fleet. Now, this is our service offering. The way to read this slide is not from top to bottom. It's best to view this as from bottom to the surface, bottoms up. From here, going to the surface. We are employed to offer offices and camp operations. Yes, we can do that. We have to know how many people would be deployed, how many people would we be accommodating. Suppose we are drilling or operating 4 rigs in one location, doing how many would you be accommodating? Oh, imagine that, ladies and gentlemen, 600 people. We have to make room for them. We have to have them well fed.
given meals, round the clock, laundry included, etc. Asset reliability, how many, we were heard earlier today, code 8 or rig repair, that is a no-no. That's when our business development people will be furious. Mike, we're not getting paid here. So our asset has to be reliable always. We keep downtime as low as possible. Of course, that is to make the client happy as well. If we are registering code 8 or downtime, that's a points against to all of us. And that we do not want to happen. Drill pipes. A 3,000 meter well, how many kilopounds or how many kilofoot-pounds of torque or pull kilopounds will we be experiencing? We have to know those information so that we will be planning on the best set of pipes that we can deploy at the rig site. Casing running, yes, we run them. Heavy lift operations, we have lifting equipment. Transport logistics, we have a specialist here from logistics. Ed, how many truckloads would you move for a 2,000 horsepower rig? 110. Imagine that, 110 truckloads. And how many days would you be doing that to complete it? 7 days. In a week's time, he has to transport them. Now, he's physically not doing that, but he is included in planning the resources, the trucking that would be required to complete that task in 7 days. Add that to the rigging up, add that to the preparation of the job site. That's about 10 to 12 days. Imagine that. So that's how busy, that's how challenging the job of the transport logistics. And then from drilling operations, our human resources would ensure that the crew operating it are properly trained. It's not just that we meet on the street. They have to have proper training as dictated by regulatory requirements of the country and as required by the client. Well site management, that's also included. One of the models that we can be exposed at or we can be considering is integrated project management. The drilling contractor can manage the other service contractors as well. Sometimes you only do drilling services. The asset would be from the client. We only provide the drilling crew. As similar to what we are endeavoring in Japan. Yeah, crewing services. And then that would lead us into either one of the three things. We drill the well construction. We either do an intervention or a workover. And lastly, we do plug and abandonment. If that is what is required for us to do. Incidentally, we are also capable of doing well engineering consultancy. Having said that, here are the risks that we should be made aware of. Now, these are the output of the previous teams, the previous groups, the geologists. They spell the risks for us, how deep the well will be, how mountainous the region will be. Now, these are also the additional input that we have to know. How deep, how deviated will it be? And mind you, that 7 days that Ed has just mentioned earlier, that's being done in mountainous drilling pads. Prerequisite is for us to have access roads, for us to do it in 12 days. And how Eileen is doing it is that we have to work 24/7. Our HR, our human resources. 2 shifts of 12 hours a day working. That's how we do it back home, in 3 shifts. 2 shifts at the site, day shift and night shift, and 1 shift on days off. In that case, it's best if we can make use of the day rate. Instead of a lump sum, instead of a footage. I think that's what's most cost efficient for all of us. Now, this is what's being prepared by a drilling engineer for the contractor's level, for the contractor side. For the safety, you have it here. We do not want Lito Daculio explaining to management that we have lost time incident. We do not want management seeing downtime every time. Okay. So given the depths of the well and given the faults that we will intersect, we are going to report to the management on how long it's going to take to drill one of these wells. By the way, this is the actual days versus depth graph, the very first slide that I have. This is an actual data that we have. The risks are not just shared. The risks above the surface are not just solely for the contractor. it's a collection of the other parties as well, such as the cementing contractor, the directional drilling contractor. Collectively, they have to work together to minimize downtime, to expedite drilling. Now, this is a game theory plan of well planning. This is what we want. Geology is good and the drilling is correct. This is a disaster. This is what we do not want. Okay? Geology and drilling gone wrong. Now, having said that, we're going to present about briefly five models for us to choose from, depending on the risk appetite of the client. The very first one is totally insourced. Classic examples what we were doing in Kenya. Everything is in-house. Everything is in their organization. The limitation of that is that technology transfer is very, very limited because everything is in-house. Flow of information outside their organization may be limited. It may be complex. And sometimes it may lead to drilling unnecessary wells just to keep the asset busy. Now, the second model that we may want to explore at is the conventional internal drilling department. The rig belongs to the operator, and then some of the specialized services are outsourced, are tendered to another third party. Now, if some of these consumables are managed by the third party, vendor-managed inventory, that's where drilling project management would come in. That's the third model, DPM. Drilling project management would come in. The inventory are managed effectively by the specialists. The fourth is just the drilling management is left to the client. And then the rig contractor manages the rest of the specialized parties. That's what the integrated project management is. And lastly, the opposite of the very first one, that's a turnkey. Everything now is delegated to the rig contractor. Now, what's the takeaway on this? Number one, depending on the risk appetite, depending on the efficiency of the cash flow, that's where we choose which model you will undertake. And then the flow of information. It has to be efficient, whichever model you're undertaking. The second takeaway on the second bullet is if you are a big, robust drilling company, you may want to undertake having an internal drilling department. Lastly, if the drilling company the operator is not that big, if they are small, you might want to outsource it. Now, just be careful, just be mindful on the retention of the information if you are going to outsource the services. Okay? Now that ends our presentation. If you have further questions on our slides, Thermaprime, please raise your hand. Where are you? They are at the back. That's one. They can answer that. Secondly, you can reach us through these channels. Contact us. And then lead us distributing our handouts. You may reach us through those channels. Okay, thank you very much. That ends our presentation.
All right, thank you so much, Michael, for sharing Thermaprime's experience. Really.
Good morning, everybody, ladies and gentlemen. Thank you for stepping in to listen to what we can share from Halliburton. My name is Sam Abraham, and I am the Global Technical Advisor for Halliburton on geothermal specific. Also, I see familiar faces out here. What I'm going to share about is a little bit on drilling bits, but what I can say from the familiar faces is how do you use these bits properly, and what are the tools that you need. Bits is one part of it, but there's a whole aspect of what you drill. And for those of you all who are listening, everybody can drill a hole in the ground. I spoke this yesterday. But what you're looking for is to drill a well in the ground, number one. And number two is get the deliverables, what you're drilling for. For example, if you see in the aspect of geothermal here in Taiwan, mainly if you look at the wells that are there, you're looking at some of it probably is on the borderline of being a conventional geothermal well, where you've got some hydrothermal resources, or you're going to EGS projects. AGS I won't touch there, but EGS and AGS projects and conventional projects. Now, what is very critical in this is you've got a rig. First of all, selecting a rig is quite important, mainly because here you're talking of drilling to depths of 3,000 to 4,000 meters deep, number one. Number two, some of them are vertical, but some of them are also going to be directional and maybe even go horizontal for a long distance. Now, the formations over here are pretty volcanic, and also you find a lot of intercalations of formations. When I say intercalations is you find layers. Many times in some of the wells you are looking for homogeneous formations, but nowadays you find intercalations where you've got a hard formation, soft formation, and how do you drill through those? Now, when you select a bit, what are you looking for? Your main challenge or what you're looking forward is, can I drill one bit and one section? However deep that section is a different story. Now, why is this very critical? Because every time you drill a well or a section of the hole, you have to reach to the TD of that section before you run casing. The number of times increase when you change or pull out to change a bit, it's going to cost you time. And if you're going to cost time, that's going to cost you money. Plus, what type of bit are you selecting? Sometimes there are formations, say in Taiwan, okay, I might call up a drilling bit company, can you provide me a bit? And we will say, Sam, the first question is, Sam, what do you have for offset data? Now, many times in new areas, you may not have offset data. So you have to make a few assumptions over there. So when you look at, say, for example, I'm now referring to Taiwan as a whole, or this region, you're looking at highly interbedded formations, number one, then hard volcanic rock. These rocks, some of the minerals in those rocks, I can almost bet you, we've seen some of these minerals that chip away a PDC bit, and give it about 2 or 3 hours, the PDC bit comes out like probably no hair on the head. Now, also you find metamorphic rocks. Now, one of the other things that you have to always consider is that for a long time, when I started drilling back in 1991, if you were to tell anybody I'm going to use a PDC bit to drill a geothermal well, say, Sam, no, that's not possible. We had to change that concept quite a long time. It took some time. Finally, we have been able to change it. And what we are doing in Halliburton is also trying to apply these same standards. For example, I worked a lot on the Poach project in the US. That's the Frontier Observatory for Research in Geothermal Engineering. What they did under the Department of Energy is finding rocks, finding bits that can drill through uniform granitic rock to get to a certain TD. But here now what I wanted to focus today on is, yes, if the rock was very homogeneous, I would be talking a different story. But here, the rock is not homogeneous. It's an intercalation of formations. So here, selecting a bit to match a formation is a challenge. Plus, keep in mind, your bit selection is quite important because before your bit actually touches the ground, the fluid flowing through the formation starts to make an impact on the formation before it actually touches the ground. So here comes your hydraulics, bit hydraulics also. Now, one of the things that Halliburton came up is with, especially in the Southeast Asian region, we looked at directional bits, especially using PDC bits. I'll show you something, for example. So here you see these bits where you've got either 7 blades or 9 blades, number one. Then you see the arrangement of the teeth on the rows. And then
what you're looking for is in this main thing, two things. One is your depth of your cut. The second is the hole being in gauge. Many times what happens, these outer gauge rows are the ones that sees a lot of impact on the formation, from the formation. And then when you drill geothermal wells, the other challenge is that you lose circulation at times. Now, what is the main challenge over there? When you're drilling, you know, you guys are everybody who does some work at home, cutting things at home, right? So if you put some water, it helps to cut things better. Now, that's what also gives us a little bit of buoyancy factor and some protection from that, all the vibration. But the moment you lose your fluid in the hole, what have you done? Your buoyancy, anything that's giving it support is all gone. So your now lateral vibrations are going to increase more. Now, if you see here, we have just taken a few examples of what we have seen in these pits. Now, if you see, for example, here, you can see these cutters, especially on the center part of the wellbore of the bit, it's still pretty good. You see, starting towards the edges of the bit, you start seeing chips and things like that. Here in New Zealand, we drill through a formation called grey wacky, which is very much igneous or a metamorphic, almost going to an igneous type of rock system. Then, one of the challenges here is, how do you, now comes the challenge in geothermal wells, especially when we are talking of EGS projects, you are trying to drill not vertical wells, but directional. Now in directional wells, when we use things like MWD and LWD, you want to make the direction or the hole that you are drilling to be very smooth in your trajectory. But many a times what happens, you start seeing dog legs. Means what happens? You build an angle, then it drops. You build angle, it drops. So when you're having that dog leg severity, you start seeing a lot of lateral vibrations and effects of that on your bit itself. Now, when you drill long laterals, when I say lateral, short laterals will drill, after drill a vertical section, then we go, so maybe 300-400 feet. But now, we are talking of geothermal wells where we're talking of almost 1,000 to 2,000 feet depth in the lateral. If you have seen, some of you all might have seen Ever, Furbo showing their well designs, where they want to drill true laterals, almost 1,000 to 2,000 feet apart, long, and then want to communicate between these two wells. So those again add challenges to how can you clean those holes. Very important there is, when you are drilling those lateral sections, what happens there is, hole cleaning becomes a very big issue. If you do not clean your holes properly, then you have a problem of getting stuck very soon. I'm sure drilling guys will tell me that, will agree to that. You start drilling the holes, you start losing circulation, your cuttings are building up in that low side of the hole. And very soon, if you all have not drilled these type of wells, let me tell you one thing. As a driller, watch your brakes. Watch that gauge on the torque starting to rise up, because these cuttings are piling up behind you. If you do not clean your hole properly, if your cuttings are not transported, you're ready to get stuck at that point. Then, one of the most important things is you want to reduce the number of trips that you do on your well. Why is that very important? Two things. That helps you to cut down your drilling days. Because every day that you drill on a well, what is your average cost of drilling per day? Any guesses? Okay, I'll give an answer. It's about $50,000 to $75,000 per day of everything on that well. So the more number of even hours that you spend on a bit, it's going to cost you more. Then, when you reduce your trip time, that's also helping to reduce wear and tear on your formation and on your drill string itself. What are the operational impacts? you have got both vibrations and your curve as you build your angle. I won't go too detail into that. Here again, one thing here is this type of bits helps you in directional course, building a directional course much more smoother. Why? Because the bits are shorter in length, and that helps you to control that. And stable bits in terms of vibration not being affecting it. I won't take much time here. Just I wanted to show here is, if you see the amount of build rate, here it's much lower, but here it gives you much better dogleg severity sensitivity when you're using these type of bits. Also, it helps you, these pads that are there, helps you to drill a better gauge hole. Now, what do I mean by a gauge hole? A gauge hole is, suppose you're drilling a 12¼ bit hole size, okay? It drills a certain hole. But if your gauges are not protected, gradually as you go through the life of the bit starts to become a bit smaller. So what happens there, you may be thinking you're drilling a 12¼ hole, but slowly as it's gone down, it's probably gone down to about a 1/4 inch less. Now, why is that very important? When you pick up the new bit, that's 12¼ hole, it has to first clean out the previous whole section and then go and drill the new section. So then people may say, hey, Sam, I thought your bit was going to give me 500 meters for this bit, but it only gave me 400 meters. Why? Because you had to go and spend additional time drilling that other section. So this is why sometimes selecting a bit, having the different parameters is quite critical and very important. Halliburton has run these in different formations in different parts of the world. I won't go too much. I'll just like to focus on, this is again what we did in terms of the goal that we had when we selected the client along with us in a collaborative manner, selected a bit. What did we achieve in that? Our goal was to complete that section, 1 BHA, 1 run. And the second is to increase the ROP. Both these were achieved. One is you drill that section in 1 bit, and the second thing is your ROP was much better. Here again, it's a combination of factors that we make, but most important is a bit that you select. There's the answer to that. 30% increase in ROP, number one, and we had the offset well there. That was helpful for us so that we could sort of gauge what we need to run in this well. One of the onshore areas in Asia Pacific, again, we have replicated the same. So what did we do here? We anticipated that this bit would drill up to about 1,000 meters. And actually we exceeded the plan that we had, and we could do it better. So what did we achieve? We achieved 44% increase in footage and about 9% faster ROP. But let me remind you all of one thing. Whenever you are choosing a bit, let ROP not be one of your criteria. But more important is drilling a proper hole in gauge, having your hole cleaned properly, and then making it to the next section. Because if you do not do that, sometimes I've had clients, I used to sit on the other side. Now I work for Halliburton, but I work for the client side also, where sometimes the client is telling me, Sam, I want you to drill faster. There is a limit to that you can, depending on how you optimize your bit performance. And this one is tracking on itself, so I won't. Sorry. So what are we finally looking to? Whenever we are making this bit selection, especially in the hypersteer, the type of bit that we have selected there, especially a PDC bit, not a tricone, what we have achieved is one is drilling one section with 1 bit, increasing the ROP from about 20 to 30%, and increasing the meterage. And most importantly, not leaving any cones in the hole. This is very important because many times you see people are wanting to drill faster. They use tricone bits or even the PDC bits. Sometimes they want to drill faster, but they are not looking at any gauges on that in front of that driller. Finally, what happens? Either you come out with 3 cones left in the well, or you come out with a bit that has had some problems. What does that add up to? You have to spend time to fish those PDC cones, tricone bits, cones, clean up your well bore before you can drill further. Just some practical aspects of why you select a bit. What did this PDC bit do for us as Halliburton? And what are we doing now as I close? We are now working on technologies. One is to improve the temperature at which these bits can work, helping to improve the optimization of our nozzle placements so that the holes can clean better. And then the third is having better gauge protection so that you have a better in-gauge hole rather than a hole that is smaller in size. Thank you for your time. And if you have any questions, maybe I can take on it later. Thank you very much.
Awesome. So my name is Bryson Iwanchuk. I'm the technical advisor for ranging within Halliburton. Just a little bit about myself. I've been involved in over 100 wellbore intercepts, some of that being foot on the ground, others just in planning processes. I've also had the privilege of being involved in the deepest relief well in history. So for the presentation today, I'm trying to bring some of the lessons that we've learned in oil and gas, primarily in wellbore intercepts, and kind of bring it into the geothermal space here. So starting off here, I have a slide just on the evolution of geothermal wells. I know we've seen this a bunch of times, so I'm just going to go through this very, very quickly. So kind of going left to right here, we have the direct use geothermal. Nothing too complicated from a drilling perspective, just drill down a couple hundred meters or so, find a geothermal reservoir, direct access to residentials. Next, we have the hydrothermal resource reservoir. This is kind of where we're at today. This is what's more or less conventional. So fundamentally, we're trying to be finding these fractured reservoirs. It's a little bit tricky to find these, as we've kind of learned throughout this conference. So it's a little bit of a costly endeavor to drill these wells, to have them flow through this already kind of pre-fractured location. Next, we're then talking kind of in the more advanced guys here, so I'll just click these ahead. So we have the EGS and the AGS systems. So the EGS, we're inducing the fractures ourselves, but the same kind of concept, pumping fluid down one well, having flow through those fractures into the other well, and obviously getting the returns that way. And then finally, this is kind of where I get involved here, is the AGS systems, or the advanced geothermal systems. So there's kind of two styles. There's the tube-in design, or the concentric cylinder. So you pump fluid down one side, it heats up, it comes back the other side. The one that I'm really particularly interested in, though, is the underground loop. So ultimately, we try to connect two well bores. We try to make an underground radiator, pump fluid from one side, it heats up, comes out the other side. So let's talk a little bit more about kind of the AGS system and some of the challenges that it has here. So this little illustration on the left here, I guess that's it, right? You have two wells, just connect them, right? How hard could it be? So we drill one well down, we drill a second well, we hopefully try to intercept it. The trouble with this, though, is we're intercepting these well bores at the deepest part. And at the deepest part, it's also the hottest part. This is an extreme challenge for us that we're always trying to mitigate. So this image just to the right of the illustration there, this is a real world example that we've done. So this guy here, it's about 5,500 meters deep, and it was quite hot, as you guys can see. So this is kind of a real world example of us drilling one of these YouTube style wells. So just another kind of point to this, wells can be drilled vertically or horizontally. It doesn't necessarily change the complexity all that much. So why is it challenging to drill an AGS? Well, it all comes down to air. So everyone likes to think they know the wellbore position of where their well is, but the fact is there's the little inclination kick here, the little bit of drift here. It builds uncertainty. This uncertainty, it happens in 3 dimensions, obviously in the depth, in the azimuth, and the inclination, and it also compounds with depth. So think of it as an ellipsoid, and it just gets bigger and bigger and bigger. And this is not only just on the target well, the one that we're trying to hit, it's also on the drilling well. So on the left here, I have a really good image. This is an AGS style well that we were drilling. It shows the ellipse of uncertainty at the interception point. And just to put this into perspective, we're trying to hit something that has the diameter of about a dinner plate, right? the ellipses of uncertainty, if it's a good well that has really good surveys, the ellipse of uncertainty might be double the size of this room. I've been in ones that are the size of soccer stadiums. So we're trying to hit something. We're basically trying to, thread a piece of spaghetti through a wedding ring, if you will, from the top of a building. So this is the largest challenge in every wellbore intercept: is how do we manage the air, right? Every well has it. We have to get rid of it. So what do? Well, we use what's called magnetic ranging. So this image has a lot going on. So I'm just going to kind of walk everyone through it. So on the left-hand side here, I have two wells. I have a drilling well and then a target well. The target well is going to be on the right-hand side there with that kind of red ice cream cone on it. So what that is representing is, as we're drilling deeper, the ellipse of uncertainty of where that wellbore could be is increasing. So from the side view, it kind of looks like a cone. So we can call it a cone of uncertainty. On the drilling well there, oh, is it? Okay, gotcha. There we go. So this blue kind of pizza slice here, you guys can all see that? So this is what we call a magnetic ranging shot. So I'm going to explain what that is. So just on the side here, a magnetic ranging shot is determining a distance and a direction between the two wellbores. So with this distance, there's going to be a little bit of air. There's going to be a little bit of air on the far side and a little bit of air on the close side. As well as when we're referring to direction, the well could be a little bit more to the left. It also could be a little bit more to the right. So when you put all those airs in together, it makes this funky shape called an arced sector, or like a chunk of a donut. It's kind of how I like to think about it. So when we're using magnetic ranging, the goal is to get this ellipse of uncertainty, how big it is, and we're going to shrink it down to that chunk of a donut. Magnetic ranging also works opposite of traditional surveys. So as surveys get bigger with depth, magnetic ranging, we actually get smaller and tighter as we get closer to it. So that's how we're able to perform wellbore interceptions. So what is magnetic ranging? Well, the textbook definition of it, if you will, it's the use of a magnetic field, either natural or induced, to determine a distance and a direction between two or more wellbores. To put it simply, think of it as an underground metal detector. That's the best way to kind of think about it. So this magnetic field can either be from existing tubulars, or it could be from a source that we deployed in the ground. So the fundamental three steps of it is we generate a magnetic field, we try to detect that magnetic field, and then we try to determine a distance and a target to that magnetic field. So how do we generate a magnetic field? Well, there's 4 ways. To put it simply, if you just have a piece of wire, if you have a piece of wire, you run a bit of current through it, this creates an axial magnetic field that we're able to pick up. If we take that same wire and wrap it around itself, we now just made an electromagnet, or a coil, or also a solenoid. Over here on the exit door, that metal lock, that's actually a solenoid right there. So they're kind of everywhere. Next, we have permanent magnets. So think of your magnets that are on your kitchen, on your fridge. These ones are a little bit more high tech, but it's basically the same thing. Think of a north-south bar magnet. So that's what we got there. And then finally, we have just the remnant magnetism that's left on tubulars. So this could be any metal. Basically, any metal that has any form of iron in it, we can detect to some degree. So that's what this is talking about. So how do we measure magnetic fields? Well, to put it very simply, we use what's called magnetometers. Everyone here has used a magnetometer. They're in your cell phones. It's how you have the compass, right? So it's a 3-axis sensor that's able to figure out a direction and an intensity at a single point in space. We take this one step further, though, and we use what's called gradiometers. So what gradiometers is if I took a series of magnetometers and wired them all together in a grid. Okay, just imagine that for a second. I'm gonna change this to sound for a second. So pretend I didn't have this microphone. If I started talking, the individuals at the front here would hear me pretty good. Individuals in the back, it would obviously be a little bit more quiet, right? There's a decay. So if we know the positions of each of the individuals, like the distance between, and use a little bit of math, we can actually back calculate out, based on those known positions, where I'm standing. This is the same way with magnetic fields. So magnetic fields have a predictable decay. We know the initial intensity of where this should be. We have multiple sensors that are monitoring the decay between multiple points. And from that, using a little bit of math, we can actually back calculate out and get a direct measurement to a target. I know it's a lot to take in, but it works. So So with this all being said, us and our gradiometers and how we make magnetic fields, we have a whole list of ranging applications and categories. To put it simply, and to break it down I'm gonna say very simply, we use magnetic ranging when we want to hit wells, and we use magnetic ranging when we want to dodge wells. That's it, put very, very simply. So there's obviously a list of applications that I could spend, an hour or two talking about, but maybe for another day. But the other thing I want to get to is we have what's called access dependent and access independent solutions. So what that means is access dependent means we need access in that target well. We need to put a sensor, we need to put a magnet, we need something, we need a target, right? So we need access to that target well. Access independent systems mean we don't need access to that target well. We're able to range without needing to access that well. So when I'm talking about this, think relief wells, right? The well's on fire, we can't get there, right? So that's kind of what I'm getting at. So every ranging job generally falls within this matrix. It sometimes takes bits and pieces from all of this, but this is, kind of a really good summary, I'm going to say, of it. So next, we have our ranging technology fleet. So starting off on the left-hand side here, we have our MGT system. So the MGT system, it stands for the Magnetic Guidance Tool. The Magnetic Guidance Tool is basically a large coil of wire. We take this coil of wire, we put it in the target well. From this, we send current downhole. It generates a massive magnetic field. This magnetic field is then picked up by the MWD sensors, and we're able to get a distance and a target between the two wellbores. Next, we have the RMRS system. The RRMS system stands for the Rotating Magnet Ranging System. The way that this system works is that directly behind the bit, we have a bit sub. The bit sub's about yay big, and it's jam-packed full of rare earth magnets. They're extraordinarily strong. So what happens is when the pumps are on and that bit is spinning, this giant magnet is also spinning. It's creating a very large, distinct field. From that, in the target well, we run a sensor, a wireline sensor. That sensor is able to pick up that spinning magnet, and it's able to figure out a distance and a direction between the two. Moving on to our access independent systems. So starting off, we have our well spot system. So well spot is it's our interception tool. This is the primary tool that we use for wellbore intercepts. It doesn't need access to the target well. The way it works is that there's a wireline sensor at bottom here, and about a couple 100 feet or so above that, we have an excitation source. And what I mean by that is we send electricity through the formation. Some of this electricity works its way onto the target well. It then goes up and down that target well, making a very small magnetic field. And from this, we're able to pick it up with that sensor. So this is the primary tool that we use for all access independent wellbore solutions. Next, we have our PMR system. So PMR stands for the Passive Magnetic Ranging System. So this isn't necessarily really a tool, more of kind of a very advanced software that we use. So what it is that all tubulars that have iron in them are going to have a little bit of magnetism left in them. A lot of non-destructive testing that they do on the threads, that's also going to leave a very, it's going to leave them magnetic. So what we're able to do is we're able to drill near the collars and pick up that magnetic signature and actually use that remnant field that's just left on it to figure out a distance and a direction between the two. So this system isn't necessarily a standalone system. It's more or less used complementary to combine it with others, but it could be used standalone depending on circumstances. And then finally, we have our Aurora system. So the Aurora has kind of overtaken our MGT system. So what it is rather than having a wireline unit that connects to a coil, we have a very large power supply on surface. We plug that power supply onto the wellhead and we shoot current downhole. This generates an axial magnetic field that we're able to pick up. So it's a limited wireline. So from our fleet here, we ultimately can use any combination or any individual one of these tools in order to drill at AGS. Every well's different, right? So we have to take in all the parameters, see what's best, temperature limits, things like that. So what I'm really excited to show is we came up with a new tool. So you guys are some of the first people outside Halliburton to see this. And the system is, it's so new, it doesn't even have a name. So we're referring to it as the Geothermal Ranging System. So it's a new concept and it's a new tool. So the basic concept is that we have two drilling rigs drilling at the same time. in one rig, we have a brand new tool, which is called the excitation collar. So the excitation collar gets connected to the iCruise rotary steerable system. Oh, I'm dead here. So in the top well there, long story short, the iCruise generates a lot of power. This collar also has internal turbines. So as we pump fluid down, it charges up. And it's a solenoid-based collar, which it actually generates a large magnetic field. So the system's designed quickly enough that we can be drilling a second well simultaneously. In that second well, we run our base star MWD, which has pretty souped up radiometers, I'll call it. Ultimately, we can drill 2 wells at the same time, continuously ranging to each other. So this is the fastest option that we were able to come up with. So it's able to eliminate the need for wireline, which is massive, and it's the fastest possible tool for a wellbore intercept. Just a few more kind of notes on it. So you guys can see the solenoid-based collar on the top there, the base star system there below. The system's designed, as I said, to work with 2 rigs simultaneously. That being said, we could also substitute out the second well with a wireline. So it's not necessarily needed, but it's recommended for speed. Some facts on this, though, is the detection range. So this tool is able to see up to 400 feet away, 120 meters. So generally, ranging systems work really good far away or really good up close. This tool is able to range the entirety of an AGS well, from the beginning all the way out to get your, the thermal gradient between the 2 wellbores, and then back and provide an interception. I then want to highlight here the temperature rating, so 160 Celsius. So everyone's eyebrows are probably going up and saying, oh, that's low, that doesn't work. This being said, this is the lowest temperature limit, like this would be the lowest limiting factor of this system, but we don't run it by itself. This system is run with insulated draw pipe. It's run with mud coolers, systems like that, which actually can keep it alive. So though it seems low, it's a number we're trying to improve. It's actually not a problem because we just need a system around it that's in place for it. So yeah, so just an update. So this tool is, as I said, extremely new. This is kind of where it's at in terms of its development. So this is a picture of it right here. We built a whole bunch of them. We've calibrated a whole bunch of them. You guys can see here, it says first field trial planned for April. So while I was flying here, it actually completed its first official trial at our test well. It was going to intercept like the well, but the rig broke and they had other timing constraints. So rather than allowing to finish the intercept, they just said, you know what, this is good enough. So it's scheduled for its first customer use in 3 months. And yeah, so it's the first tool designed specifically for AGS. That's all I got for you guys.
Thank you, everyone. So I'm here presenting on behalf of Yusuf because unfortunately he had another commitment. But he did send his warmest regards to all of you here. So my name is David Tabarat. I'm part of the solutions engineering team from Indonesia. And right now I'm trying to presenting these topics, which is LWD data acquisition. In regards of the caliper and drilling mechanics also, as a new approach for the geothermal drilling operation. This is a case study from one of our well in Indonesia, specifically in Sumatra. Okay, before we go deeper into the analysis, let me introduce you a little bit about the LWD data, the LWD system, right? So basically, this LWD stands for logging while drilling. Is simply combine the conventional wire and log into the drilling BHA. So you can have more efficient operation where you do not have to pull out the hole and then running the wire and log, right? So you can run simultaneously using the drilling BHA. So in here, this is the typical, very basic LWD setups that we can run in the geothermal wells. The red one is the standard MWD. We call it MWD because it's measurement while drilling, basically only transmitting the wellbore survey data downhole, right? Consisting of the measure depth, inclination, and azimuth. This is the MWD part. And then on top of that, we also add the PWD, or annular pressure while drilling, where we can also check or see the ECD, the equivalent circulating density. And then on top of that also we can also include the vibration sensor, right? Where we can see the modes and the mode shape of the vibration downhole. And then lastly, we can also include the temperature collar or temperature sensor into the drilling BHA. Okay. In LWD service specifically for the geothermal, we are using this electromagnetic telemetry, right? So why we are using this one, the electromagnetic, because of we have two different things, two different telemetry system. We can use this mud pulse system, which is we are using the differential pressure of the mud inside of the string, and then we can have this electromagnetic. So why we are using this electromagnetic? Because of well, in geothermal well, we are seeking for the low circulation, right? Because that's basically the potential fractures of the reservoir. So this EM, this electromagnetic, it's much more independent in terms of the return flow of the mud, right? So once you hit the total losses and you start mixing fresh water with air, mixtures of air, this EM is still can have data from downhole, right? So basically this EM having two antennas, the surface antenna in surface, and then downhole antenna. We will get into the details of the BHA itself. Okay, so I'm speaking of the case study. So this is the well architecture of this case study. So basically this is, we are having 4 different hole sections starting from 26 inch, and then we're kicking off in 7.5 inch BHA up to 30 degrees inclination, and then we drilled with 12.25 here, and then 978 as the last hole section until TD. The blue line represent the plan, and then the red line represent the actual trajectory, right? So in this well, where we use the LWD is on the 12.25 hole sections. These yellow lines represents the area we run these LWD tools. So this is the side view of the well, and then this is the top view of the wells. If you can see, the blue as the plan, and then the red is the actual one. Okay, I'm gonna jump into the configuration of the LWD tools. So basically in this well, we are using the mud motor BHA, right? And then on top of that, we have float sub and sub laser. So this small figure is just like simplify the figures of the tools below our LWD. So on top of our motor and stabilizer, we also have this acoustic caliper collar. We call it ACAL. And then PWD stands for the pressure well drilling. And then the HSIM, our processor. And then on top of that, we have our PCDC or directional sensor, right? On top of that, we have this EM antenna sub, where this one is part of the EM telemetry things. Okay, with the typical sensor distance, the PWD, this one is around 18 meters away from the bit. And then acoustic caliper is around 15, and then PCDC around 22, sorry, in feet, 22 feet. So I'm going to jump into the first analysis, which is showing the caliper data analysis. Like I mentioned to you, we are running this acoustic caliper. So basically, this acoustic caliper sends signal like acoustic impedance to the formation, and then record the time travel between transmitting and then receiving, right? So that happens in milliseconds. So all of this data spreads represents the feedback in milliseconds of the acoustic signal, right? So all of this you can see it's all scattered, but if you can see here, the gray line is the average one, right? So by this we can conclude which are the correct data, right? So if you see here, this is the 12.25 hole section. We can set that one as a 12.25 hole sections plus minus, and then all of this one is the noises that the drilling condition made. So after we have standardized or bench the errors, right? So we can also filter out. So by this, we can filter out the actual conditions during drilling, right? So on the left-hand side, this is the real-time data from the acoustic caliper. And then the right-hand side, this is the one that we have filtered out based on this statistical data analysis, right? If you can see, in the real time, we have a lot of noises. That's why it's showing like very, very scattered. And then after filtering out and screen out using this methodology, we can see it's quite smooth, right? So you can see a couple of interval that severely overgauging or wash out, right? So by this also we can get data. The average hole size indicator is around 13.3, which indicates we have, in average, we have like overgauging around 1 inch because the bit size is 12.25. Okay, the second thing is the drilling mechanics data analysis, right? So like I mentioned to you before, we are using the EM. But as only for differentiation, the 7.5 inch, we are using the basic EM. If you can see here, using basic EM, the PWD data or ECD data is less dense compared to the 12.25. Because in 12.25, also because we have our HSIM or processor, we are using this EM PPM, much more higher data rate compared to the previous sections, which is 7.5 inch. So if you see the comparison for the ECD itself, it was like more dense and then more details compared to the previous hole, right? So this is because of the EM PPM that we use in the 12.25 hole sections. Okay, the next one, we also looking into the vibration, right? So some of you may know the vibration methods or modes consisted of 3 axes: the lateral vibration, the torsional, and the axial vibration. By these 3 different axes, we can see 9 different type of vibration in here. The combination of the axis and then the frequency where the vibration happen. Right? So that's the basic one. So we also develop our own system, which is we call it the traffic light system. Green, yellow, and red. Right? The green represents we are in the safe condition. The vibration is quite low. The yellow is intermediate, and then the red one is quite severe or high. Okay. So, So by having this traffic light system, we can easily identify along the whole interval in here where's the spot that we have like high and very high vibration, right? If you can see here, we divide it into 6 different sections or area. Sections 1, 2, and 3, it's relatively quite low, but we see some high vibration in here, but it's still relatively low compared to the section 4 and section 5, right? Because the magnitude you see, the magnitude is quite different, and then this one is quite high compared to the section 1, 2, 3, and 6. So that's why we start putting attention to these 2 different part of the formation, which is number 4 and number 5. Okay, I'm going to go into the methodology framework of this analysis or study case. So the methodological framework, we separate into 5 different, process. The first one will be the formation identification, where we see the formation lithological by doing the MEB or methylene blue test, right, to check the reactivity of the formation. The second is the distribution of the drilling parameter, where we map the parameter that we input and then the result or the parameter output, which is ROP, vibration, and so on and so on. The third one will be the statistic, where we also see the statistical data where the vibration is happen and then the spreadness of the vibration. The fourth one will be the burst file, where this one is the total data of vibration that we receive from the downhole, and then the vibration mode we can conclude from the burst file data. Okay, like I mentioned to you, we put more attention in details for the formation number 4 and number 5, right? Because we see the magnitude of the vibration is much more higher in these 2 parts of the interval, right? Okay, so we apply the methodological framework, right? First one, we identify what the type of formation. And then we also include the MEB test, right? And then the second one, we see also analyze the drilling parameter and then vibration distribution. The third one, the ROP and vibration statistic. If you can see, the average and peak is quite green, but the torsional surprisingly red, right? So by this, we can conclude the type of vibration, right? So mainly in these two area, we see or we expect to have this torsional resonance or beat chatter. Okay, and then we also looking into the caliper data analysis in terms of the subsurface thing. If you can see here, we also separate that one into 4 different area because we see the severity of the overgauging hole, right? So by this we can conclude area A, B, C, and D having like quite severe of overgauging, right? So correlate with the formation, what type of formation? The formation A, apparently the lithological is intrusion, and then formation B, C, and D is more related with altered volcanics, and the lithology is silicic tuff, right? So we can see where is the typical wellbore breakout happen in terms of the lithology. Okay, so by that, the result is, after we see the vibrational responses compared to the drilling parameters, right, we can optimize the drilling parameters. For example, this XXE05 in here, we reach more higher ROP compared to the offset wells, which is XXE02 and XXE03. Why is that? Because we are confident to put more wet on bit. So in offset well, we play around 20-25 kilopounds because of the vibration and so on and so on. But in here, after seeing the response, we are confident to put up to 30, right? So that's why we can optimize the drilling parameter and then get more ROP. That's part of the improvement because of these vibrations sensors, right? And then for a future application, we also realized that during drilling, we only have one stabilizer just below the acoustic caliper collar. So that's why all the noises that we see before, that's coming because of this poor stabilization, right? So for the future sake, we also plan to have like additional stabilizer on top of the acoustic collar, so we can also reduce the noises during drilling, right? So for the summary, so this methodological framework is provide us valuable data, right? The first one will be the drilling parameters in summary, right? What is the input and then what is the response for the output? And then the second one is the vibration phases characterization. So we can easily see what type of vibration during drilling, right? The third one is the subsurface insight in regards of the fractures and then the presence of the smectite clay. So maybe some of us know smectite clay is quite dangerous because it can easily react with the fresh water, right? And then the fourth one, it's also giving us insight on the problematic geothermal intervals. Okay, so another summary and the future potential enhancement. The first one will be the drilling parameters roadmap, because in here we can see and benchmarking the drilling parameter in terms of the vibrational and then downhole calipers data. And then the second one is the effective real-time display for the vibration and PWD readings. The third one, the vibration methodological framework can be enhanced also, and then at the same time we can improve also the borehole drilling strategy, right? So as we know, the discussed case studies discovered in particularly altered volcanic formation, which is related with desit and silitic tuff. And this also bringing value to a first step to become machine learning or AI, right? In conclusion, for the LW trial in XXE05, it's given us a good result, both for the real-time transmission and recorded acquisition. And then the EMPPM telemetry given us a very dense data rate, yeah, for LW data. And then we still have room for improvement, yeah, for the BHS serialization and time filter traveling. Okay. And then for this LW data can be analyzed for both drilling operation and then subsurface analysis. The last one, in here, this case study is very important for us because it's open up the feasibility of hazard mitigation in terms of cost saving from potential stuck pipe because of this problematic zone. Okay, I think that's all from my presentation today. Any questions? Oh, is it clear enough? Okay. Okay then. Okay, so thank you.
Okay, hello everyone. My name is Xavier from Nago Water, Taiwan. Since today we don't have too much time, so I will introduce the history of the Nago Water in Taiwan quickly, and to save time to the following section and technologies part. So Nago Water started a journey in Taiwan in 1988. Originally, we are focused on providing the water treatment technology for chemical industry, including the boiler water and cooling water and the chemical cleaning. Okay, so our target customers like the petrochemical, steel, and manufacturing, especially like the CBC, Formosa Group, and China Steel. Okay, in the 2000s, Nago established the formal subsidiary in Taiwan. We call it Nago Taiwan Limited. At that time, we also expand our service into the electronic and semiconductor, food and beverage, and biotech. And also in 2011, Nago was acquired by Ecolab. So now you can see we have like our name is like the Nago Water and Ecolab company. Yeah. And we also deploy either 3D tracer technology in Taiwan. 3D tracer is the digital smart water management system. And so currently we also use this technology in our petrochemical customers. Okay. So from 2023 until now, we focused on the geothermal water treatment. Also, we also leveraged our global development experience, also replicated the successful case in Taiwan. So while everyone is focusing on exploration and drilling, you can see, but based on our past operating experience, we noticed that the scaling and the corrosion will impact the geothermal power plant efficiency. So that's why today we want to share our technology with you. Yeah, that is the introduction. So the next one, my colleague Fritz will introduce the technology in detail.
Thank you. Good morning, everyone. So the title of the presentation is Understanding Geothermal Chemistry. So potential chemistry-related challenges after drilling. So you have drilled your wells. So you already drilled your wells. You already put up your plant. So what happens next? So the goal is to maintain the output, right? So we have seen wells, for example, wells at, let's say, 10 megawatts in a span of 6 months, completely shut because of mineral scaling. So you can see here that the difference between geothermal and conventional power is for geothermal energy, you have to use of whatever fluid that you will find downhole. And normally, these fluids are saturated with minerals. That's why we need to understand geochemistry because it affects how we will utilize the plant. So it is believed that mineral scaling is one of the biggest challenges in terms of utilization for a geothermal facility. So it's one of the biggest limiting factors. And what we want, since we know that geothermal is a sustainable source of energy, what we want is how can we further reduce the cost? How can we make this more sustainable? So this is where management of mineral scaling comes in. Not just mineral scaling, but also corrosion challenges. So the key word here is prediction. Prediction and prevention of possible geochemical challenges are critical in maximizing the output of your geothermal facility. Okay, don't be surprised, don't panic. This is the second time in a long time that you've seen a periodic table. Okay, so these are the common elements that you will see in a geothermal brine. So it's a cocktail of elements. So you have sodium, potassium, magnesium, calcium, manganese, iron, aluminum, silica. Silicon is one of the most common minerals that we're seeing. Also, now we are seeing a lot of arsenic and antimony. And there are various factors influencing scale formation. And we can narrow it down into three. So first is temperature. There are minerals that are more soluble in hot environments, in high temperature environments, and there are minerals that are more soluble in lower temperature environments. Also, chemistry profile. Of course, scaling is a function of mineral concentration. Some scales are dependent on pH and also chemistry interaction. So some elements compete with another element, forming another type of mineral, and also some minerals combine with another mineral to form a much harder mineral, a much more challenging scale. And reaction and induction time. So this is a typical flash binary plant. So we know that the hottest part will be at the production well, because this is our source, the reservoir. So the second, the production well is the highest temperature one, and then going to your reinjection systems, either hot reinjection well or cold reinjection well. What can we say about the temperature profile? So as we go from the production well to the reinjection well, of course, temperature declines. And we know that temperature is a factor in mineral scaling. Pressure declines, and if there is decline in pressure, there is what we call flashing, right? So what we get from production wells in liquid-dominated systems sometimes are, most of the time are two-phase fluids, combination of liquid and steam. So if your pressure continues to decline, part of that liquid turns into steam. What happens with the minerals in your liquid phase is it becomes more concentrated. And concentration is a factor also for scaling. So the scale formation in geothermal facilities can be summarized into 4 steps. First is achievement of supersaturation. So your system needs to be supersaturated first for scaling to happen. That's why we have this term called saturation index. So saturation index, we calculate what is the scaling tendency of a particular mineral. If your saturation index is less than 1, meaning it will not scale. If your saturation index is equal to 1, meaning it is saturated with respect to your solution, there is possibility of scaling. And if your saturation index is above 1, it means that your system is oversaturated. So higher than you're almost sure that it will scale up. So your conditions should achieve supersaturation, and it will start with what we call nucleation. So there will be like small particles in your system, and it will act as seed for your minerals to grow or for your scales to grow. And then your crystals will grow. And then when it's big enough, it will precipitate out of your solution. And you will see the white deposits that you see in your pipes. So these are the scale build-up. And we know that in geothermal, flow is directly proportional to output. So if your pipe is blocked, your flow goes down, your output goes down. So this directly affects your output. So what we do is we developed a software called Geomiser. So this is a modeling software specific for geothermal. So we input mechanical, operational, and chemical parameters. And it will predict at what part of your plant scaling could potentially happen and what scale. So it will be able to generate a saturation index versus temperature plots, for example, of silica. For example, here, this is arsenic sulfide. So it will be able to identify what scale will form and at what part of your plant. So production well scaling, I think this is where the case of Taiwan will be, I mean, the scales that I will show here is more applicable to the cases that you have here in Taiwan. So our team were able to analyze some of the wells, some of the existing wells, and we can confirm that there is challenges in terms of calcite scale formation. So crystalline calcite or aragonite. So calcite is calcium carbonate. So this one, it has a retrograde solubility, meaning it is more soluble in lower temperature and less soluble in higher temperature. So in that solubility, where do you think calcite usually forms? It's in the production. Yes, it's in the production well. So it is the solubility is lowest in your production well, in your hottest zone. So what happens is, so before you bring your fluid to the surface, it is still single phase. As your fluid rise up, so your CO2 is being released into the solution. And what happens is your pH increases. So calcite is more soluble in acidic conditions. But once you release the CO2, it becomes more basic. It becomes more alkaline. So it pushes the reaction forward. It pushes the reaction forward, forming more calcite deposits. That's why anhydrite is calcium sulfide. It is same deposition behavior with calcium carbonate, but this one forms in high temperature regions. It is not dependent on pH. So usually you see anhydrite in the deepest portion of your well. So typical scaling location is in your production well here at the flash point. So what we do is you incorporate your treatment method when you do your well design. So usually the way we address calcite, if we are going to use an inhibition system, is to dose an anti-scalant before the flash point. So you dose the solution before your fluid flashes so that it can be incorporated in your fluid. So aside from calcite, three major scale formation in geothermal are silica, which is very common, metal silicate, and metal sulfides. So silica in itself, it is soft. So if you see amorphous silica, it is white in color, and it's very soft, and you can easily remove it using water jet. But in some fields, they are expecting silica scale, but they're getting hard. Hard scales, the color is gray. So what is the meaning of that? So most probably, that scale is combination of silica and metal ions, forming metal silicates. So you see, amorphous silica alone is easy to manage. It is easy to remove. But if you have metal silicates, the morphology changes. It becomes harder. So silica is dependent on temperature, pH, and concentration. So it is more soluble in higher temperature. That's why it is not common to see silica scaling in production wells. You often see silica scaling in reinjection wells and also in binary systems. So in binary plants, in your preheaters, in your vaporizers, you can see silica scaling. So metal silicates, iron silicate, same behavior with amorphous silica, but magnesium silicate, it's different. It is less soluble in high temperature environments. That's why in systems where you have intrusion of cold water, you can see smectite, which was mentioned in the presentation earlier. So this one is also pH and temperature dependent, and metal sulfides. If your system has high H2S, there is high tendency of metal sulfide formation. So how does silica deposit? So it starts with monomer. So the way silica deposit, we call it polymerization. So it starts with monomer, silicic acid monomers. It will form into polymers, and then it will grow and grow until you have silica colloids. So this is still not visible to the naked eye. And then these colloids will aggregate, and then once it is heavy enough, it will drop into the solution, forming your scales. So, yeah. So how do we inhibit silica? How do we manage silica scaling? Common method is called pH modification. So you add acid into the solution to delay the polymerization. So the polymerization of silica, it is catalyzed by hydroxide ions. So hydroxide ions, so if your system is near neutral to slightly alkaline, so you have a lot of hydroxide ions, so what happens is your acid gives a proton into this solution and neutralizes your hydroxide ion. So it delays the polymerization. But the challenge is in acid treatment, you have a very small window. So slight addition of acid can shift your pH drastically. And if you have too much acid, it contributes to corrosion. If you have less acid, it contributes to scaling. So you need to balance that one out. And we have seen that in some treatment facilities that they're doing pH mod, they tend to form metal silicates or iron silicates and iron sulfides. So you are possibly addressing silica, but you are creating another type of scale. So that is the challenge for pH mod. Another one is the use of polymer inhibitors. So you incorporate the inhibitor in the polymerization phase. So you incorporate the inhibitor here so that the monomers will not form polymers. So those are the two chemical strategies to address silica. Next is corrosion management, which is a common issue as well in geothermal, especially in areas where the fluids that you have drilled are acidic. So there are different drivers: process conditions, of course, temperature, pressure, and changes in conditions. So we know that temperature, corrosion rate is, if not directly proportional, so it is exponential in terms of temperature. Process constituents, so high salinity, high suspended solids can also be factors in corrosion, and it can affect both your wellbore and your surface facility. So there are different types of corrosion. Common in geothermal will be general corrosion, pitting corrosion, and also stress corrosion cracking. We have seen this one. flow accelerated or flow enhanced corrosion. And the types of corrosion based on corrodant: sweet corrosion driven by CO2, sour corrosion driven by H2S, acid corrosion driven by HCl. So as I've mentioned, this is being affected by temperature, pH, of course, salinity, and the corrosion products. So, okay, so corrosion reaction, it's a redox reaction. So in normal conditions, your pipe will form a protective magnetite layer. So this is iron oxide. It's the what we can say the natural passivation film of your system. So if it is being subjected to different factors like turbulence, changes in pH, H2S, your magnetite layer is being transformed into another type of iron and oxygen containing compound, which is hematite, and in some cases, derivatives of iron oxide. So some of the approaches that we use, same with how we address silica, we use adjustment in terms of pH, but now we're using caustic. We raise the pH of the well to become less acidic, but the drawback of that is you are introducing another problem, which is scaling. So we know that scales are pH dependent. And another one is the use of filming amines. So you dose corrosion inhibitors or filming amines in your system, and it creates a passivation film on the walls of your pipe. And the benefit of that, it prevents your corrodants into getting into the surface of your pipe. So it's a protective layer to prevent or lower corrosion rates. So, yep, that's all for our presentation. I hope you were able to learn something about mineral scaling and corrosion. And I know that Taiwan is very aggressive in their geothermal prospects, and we believe that prevention is really the key. And we are here to help in modeling and simulations. Thank you.